For CP Wang, this sort of lateral problem solving has been integral to the success of the project. Their aim is not just to be the highest, but to be their innovative best.
Let me put it this way, it's not like the Wright brothers when they invented the airplane. Today a lot of people knows how to build an airplane, but it's how good it is matters.
The design of Taipei 101 requires unique engineering to facilitate a unique shape. But the next challenge facing designers pushes this engineering to the limit. Here at the Kaohsiung China Steel Plant, some of the most high-tech steel manufacturing techniques in the world are being used to build the various elements of 101's groundbreaking megastructure.
The basic idea of this building is so-called double tube structures, which means we using the steel frame to create the outside tube, and then we using the steel frame and the concrete columns to create inner tubes.
The steel used in Taipei 101 needs to be soft enough to weld, hard enough to carry the building's awesome bulk, and pliable or bendy enough not to weaken or break if it's rattled by an earthquake. Each of these requirements demands a different type of steel, a complex chemical cocktail of carbon, alloy, and refined iron. More carbon makes it stronger, but too much and it becomes stiff, brittle, and hard to weld. The Kaohsiung plant develops 5 different kinds of steel for 101, each with a specific flex-to-strength ratio designed to suit its purpose and position in the building. The challenge for manufacturers is to make perfect steel into perfect components for 101 each time, every time, day after day. Starting with the raw materials, massive blast furnaces push out 10,000 kilogram ingots of refined steel. The ingots are near liquid hot, 1200 degrees Celsius. An elaborate system of hot rollers and purification baths torture and squeeze the giant blocks into 90mm thick flat plates. Precision, control, and consistency are crucial. Any imperfections mean weakness, and any weaknesses could be fatal for the mighty 101 megastructure. Patterns, ID numbers, and cutting are all controlled by computer. This plant uses more electricity every day than a small city. From start to finish, each super column box section takes 4 months to make. The final product is big enough to park a car in, weighs as much as 90 tons, and is as tall as a 2-story building. Each of 101's super columns will need more than 50 of these box sections. That's more than 400 for the entire building. The next challenge facing builders will be to put them together. The integrity of 101's megastructure requires the super columns to act as single units. But joining 30 90-ton box sections into one seamless unit has never been done before.
An earthquake strikes. Shockwaves tear across the island. Taipei 101 shakes violently. Anything not firmly attached crashes to the streets below.
But three factors combine to make this project not only the tallest and most visible in the world, but also one of the most difficult to build. Taipei City is an inhospitable place to build a skyscraper. Beneath the earth, a thick layer of soft clay demands uniquely designed foundations. While above ground, the threat of earthquakes and typhoons requires a level of engineering and construction never before achieved. The solution will combine two revolutionary systems. First, a braced megaframe joined to 8 super columns filled with a mixture of steel and concrete. And a tuned mass damper, a giant pendulum, the weight of 10,000 people, designed to oppose the effect of wind. The combination of these two concepts is groundbreaking.
when wind hits the building really moves.
Yeah.
And it starts doing all that for a long time. It makes people uncomfortable working in the building. So what we have designed is this. If you would please take that down.
Okay. And this is more...
Replace this with this. Yeah, the purpose
This has got a ball in it.
This is our damper, actually the heart of the building.
Wang explains his metal ball in this demonstration is in an oil-filled tube. This best represents the oil-filled shock absorbers attached to the giant damper.
So I'll mount that in. So this is now with your damper in.
Now the wind is blowing again, and
wow! So it doesn't stop it moving, but once it started moving, it takes the violence out of the movement. It doesn't accelerate or slow down as quickly. It's a more gentle feeling. I suppose what it's doing is giving you a better ride up here, isn't it?
Buildings are for people to use, so if we cannot make the people comfortable, we don't have a good building.
In 1951, Hugh de Haven files a patent for the three-point seatbelt, and car passenger safety leaps forwards. 2 decades later, the inertial reel safety belt is introduced, initially by Volvo and Ford. It leaves you free to move around, only locking under sudden movements. It uses the very same property of inertia that Hugh de Haven realized caused injury. Inside an inertia seatbelt sits a heavy steel ball. When a car is in a collision, the inertia of the ball means it will move independently. The moving ball hits an arm that pushes up and triggers a process that locks the belt. Inertia is also harnessed in the giant 600-ton steel ball suspended at the top of Taipei 101. When the building sways, it swings like a giant pendulum. It then pushes against oil-filled shock absorbers or dampers that dissipate. On the 3rd of October 2005, Typhoon Long Wang blasts hurricane-force winds across Taiwan and presents the damper system with its first serious test. This film shows the ball in action as the 110 km/h winds blow that day. As it begins to swing, the giant oil-filled cylinders take up the energy from 500 tons of swinging steel. This extraordinary footage, filmed on a cell phone, reveals the ball damping 545,000 tons of skyscraper as she sways in the typhoon.
To keep 101 standing in a major earthquake, engineers develop a complex internal megastructure. The central core of the building is connected to 8 incredibly strong supercolumns by a network of horizontal outrigger trusses. The supercolumns act like a giant flexible spine, enabling the building to flex and move if it needs to, but not break. Although the idea of supercolumns has been used in other buildings before, the size of 101 takes this engineering to an entirely new level.
Thank you.